Hi Syed.
Hi Rohit.
Hi, how are you doing?
Yeah, I'm doing great. How about you? Really excited to
I'm
be
very
here.
good. Yeah, we are all excited to have you Syed here, and people are waiting for your session, and we are totally pumped up. Uh, Before you, we had Niloshima, and now it's you. So,
Yeah,
would you like to give a quick intro about yourself, like what you're doing and what your session is going to be today about?
yeah. So, guys, I am Syed Farhan, founder of QPower Research and also Microsoft Learn Student Ambassador. So, today my talk is going to be a mixture of quantum computing and machine learning. I'm going to show you how you can do machine learning in quantum systems. So, really excited to be here, guys, and so should you because it's a new topic out there.
Awesome. So, Syed, I can see your screen being shared, so I'll put it on screen.
Yeah, sure.
Sure. It's like
Okay, to confirm, is my screen visible?
yes, Syed.
All right, Rohit, can I get started?
Yes, Syed. Yes. Are you able to hear me, Sayed?
Yeah, can I get
Yeah.
started?
Yes, 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 you can.
All right. So, hey guys, let's get started with the quantum machine learning session. To start off, let me give you the discussion points that we are going to have today. I'll start off with the introduction to quantum systems, since most of you in the audience might be new to this topic. Then I'm going to introduce you to qubits, which are the basic building blocks of quantum computing. And then I'm going to compare it with the basic building blocks of classical computers, which are bits. Then I'm going to talk about a phenomenon which is only possible in quantum computing or in quantum systems, that is quantum entanglement. I'll show you a little bit a piece of code using Q sharp, and then I'm going to show you a QML intuition for the same, and then compare it with the machine learning paradigm, the classical machine learning paradigm that we have. I'll talk about a few applications of QML and a small demonstration of a classification, a basic classification using Q sharp. Let's get started, guys. So, quantum computing has made the headlines in the past few weeks, in the past few months, many number of times. So, the recent one being that IBM promises a 1,000 qubit quantum computer by 2023. This is actually a huge promise from IBM. And then we had Honeywell a few weeks back. Honeywell had also announced saying they're launching a 64 volume quantum computer. Just after a few days of Honeywell announcing that, IBM also announced saying that they have a cloud accessible 64 quantum volume computer. So this shows us that the quantum computing domain, or the domain of using quantum computers in everyday applications or in applications in real life, is becoming more and more popular. People are investing in this, and this is a domain which actually shows promise for the future. So here are a few applications of quantum computers. So this was taken from IBM.com. The white oval which you see in the middle is nothing but the easy problems, which are very easy for the classical computers to solve. And the light blue oval which you see are the hard problems for classical computers. But the dark blue oval, which you can see on the screen over here, are nothing but which are quantum possible. So a few of the problems cannot be solved by the classical computers. A few problems like optimization problems that can easily be solved using shallow circuits. There is a quantum advantage to it. Problems like factorization can easily be solved by quantum computers, while it will be very difficult for classical computers to solve them. Then we have various applications in quantum chemistry. We have applications in machine learning, and of course, simulating quantum systems, drug discovery. These are all possible with quantum computers. So I'm just giving you a brief introduction of where quantum computer can be used, so that you can get pumped up into this particular new technology. So to start off, classical computers are nothing but the computers which use bits as the basic building blocks of information, which are zeros and ones. So you would have seen the Matrix movies, the bits moving across the screens, right? So that's classical computers. The most complicated games that you play today are are using GPUs which process these bits only, zeros and ones. And what have we built with these bits these days? So the basic building block of a quantum computer is a qubit. So qubit is nothing but the building block wherein the unit is in a superposition of both states, 0 and 1. So a qubit is represented using this ket notation. Let's assume the qubit is psi. So this qubit can be in a superposition of both 1 and 0 states. So it's like saying that a particular unit can be 1 and 0 at the same time. That's where the exponential speed of quantum computers also comes into picture. So here's a small example of putting a quantum bit into superposition. So if you have an off state moving through a Hadamard gate, which is the hedge gate, you get an on and off state, which is nothing but a superposition of both the states 0 and 1. And then finally, if you pass it again through another Hadamard gate, you get back whatever was passed through the earlier gate. So this is a small example of how you can, achieve superposition, a simple superposition using qubits. So let's talk about exponential speed up. So if you have, for example, n bits, then you can have 2 to the power n states possible, 2 to the power n, quantum states possible with these n bits. So to give you a small example, if you have 2 bits, then the 2 to the power 2 is equal to 4. So you have 4 states possible, but if it's 10, then we have 2 to the power 10, which is 1024 states possible, which means that you will be able to calculate, or you will be able to use the exponential space of quantum systems, exponential Hilbert space, to actually compute something that you want to. That's where the exponential speed up of quantum computers comes into picture. So before I move over to quantum entanglement, let me talk about measurement. So as I said, this is how a qubit is represented using the ket notation, wherein we have the psi, this kind of a line followed by a greater than sign. So if you're measuring this qubit, for example, if a classical system is actually going ahead and seeing what the value of the qubit is, you're peeking into the value, you get back a classical bit. So it will no more be in superposition, but it will lose its state, and you will get back either 0 or 1. So that's another property of quantum systems. So if you are to somehow interact the classical system with quantum system, you will have to measure the state of the quantum system and then do some processing in the classical state and then give back the state again to quantum system. So that's how it's done. So the quantum state collapses the moment you measure it. So another, the phenomenon that I want to talk about is quantum entanglement. As said by Einstein, quantum entanglement is spooky action at a distance. It is actually, because if you have 2 different qubits and you're somehow entangling them, you're doing something to them so that they're related, and then you separate them out. For example, you take 1 qubit to the moon, you keep 1 qubit on Earth, or if you take 2 qubits and put it at the ends of the universe. The universe is expanding at a faster than the speed of light. So light cannot reach, or there is no way you can communicate between these 2 qubits with normal physics. But with this quantum entanglement, if you somehow measure the first qubit, the second qubit will be related. The answer will somehow be related to the first qubit. It'll either be the same or it's going to be the opposite. If it's 0, it's going to be 0. If it's 0, it can be 1, depending on the type of entanglement that you have. So a small example, if you have 2 different qubits, you're measuring the first one, it comes out to be blue color, you can assume it to be state 1. Then the second one will be the opposite state, because it is entangled in that way. And the small circuit for it is, as you can see on the screen, we have 2 qubits, Q0 and Q1. These are the ket notations for these. And then you're applying a Hadamard gate, putting qubit 0 to superposition, and then you're applying a controlled NOT gate. It is almost similar to the NOT gate, but it uses a control qubit and then puts the other one into the, it negates the other qubit. So you're actually entangling both the qubits together using this simple circuit, and that's how quantum entanglement is possible. A small code for quantum entanglement with Microsoft Q#. So assuming you're defining 2 qubits, Q0 and Q1, and then you're setting the qubit states of both the qubits with an initial state and with the 0 state, and then you're applying the Hadamard state as was seen earlier in the previous slide, and then you're applying the C0 gate, which is the control NOT gate, which was again seen in the earlier slide, which puts both the qubits in entanglement. And then finally, you're measuring the value of the first qubit using the M function. So this entire thing was wrapped inside an operation. So what are operations in Microsoft Q Sharp? Operation, like we have functions in classical, classical programming, we have operations in quantum programming. It's like the functional counterpart of classical systems in quantum systems. Then you're finally measuring it, and you need to measure it again and again, because quantum systems are inherently probabilistic. uh, so that's how you put two qubits in entanglement, in quantum entanglement, using Microsoft Q Sharp. So let's move on to machine learning. So in today's talk, in all whatever the other speakers had spoken about, or the machine learning, classical machine learning, which you actually look at, falls into the first category, wherein the y-axis is nothing but the data generating system, which could be the classical, the classical bits we are actually feeding into the classical computer, and then the data processing device. The processing device can be a classical device, or it can be a quantum device. So what we currently use is classical data with classical computers. So it falls into the first category. But today we are going to talk about the second category, wherein we have classical data, which is fed into quantum processors or quantum processing device. And then we do the analysis. There are different other ways also possible, wherein you have quantum data and being processed with classical systems, which is very rare, and quantum data processed in quantum systems. This also has great applications, but it is beyond the scope of today's talk. Let's have a brief overview of how the classical data with classical processor works. So we define a model. Everyone knows we can define a model with PyTorch or Keras or TensorFlow. We have weights and biases which can be trained. So you pass in the training data, you train the model, and then the model makes predictions on unseen data, on the test data, or you validate it later on. And then finally, the updated weights and biases which you get will be updated in the model, and also can be used for training the model once again. So this is how a CC loop works. So now if we compare it with a CQ loop, wherein you have a hybrid quantum classical system, so the first step would be to have quantum embeddings. So you're going to feed classical data to it. You're feeding classical data into the quantum computer. You need to map it to the quantum computer itself, wherein the classical data is converted to the quantum data which the quantum computer can understand. So that's nothing but preparing your data set. That's the first part. And the second part is nothing but you are actually doing the machine learning here. You're actually doing the evaluation using a variational circuit. So the second part is the quantum variational circuit, and that is where you have these parameters, phi 1, phi 2, phi 3. So these are the parameters similar to the weights and biases which we had seen in the classical counterpart. And finally, once the data is being measured outside of this, you're measuring the data using the measurement tool. And then finally, you get back classical data. You're using the classical optimization loop. So this optimization can either be gradient based, or it can be approximation based. You're doing the approximation, or you're basically optimizing the parameters and then updating the gradients and updating the parameters back again. So this loop, which is nothing but a hybrid quantum classical system, is proves to be really beneficial to certain problems which classical computers cannot solve. So a few applications of where QML can be used. So various companies like JP Morgan and Chase and Goldman Sachs, Morgan Stanley have partnered with IBM for portfolio analysis in finance. So this proves to be really helpful if you're using quantum computers for doing analysis of financial markets. And it has shown a lot of, a lot of futuristic goals and a futuristic ways by which we can analyze the financial markets. The next type of problem is classification and optimization problems. A small example would be a support vector machine. So if you have two-dimensional data and it is not linearly separable, so if you had to separate them, you had to draw a circle. It's not linearly separable. What you can do otherwise is shift to a higher dimension. This is nothing known as the kernel trick. So I'm sure you must be aware of the kernel trick in support vector machines. You move to a higher dimension, and then you have the hyperplane, which is nothing but a two-dimensional plane to separate the data. Then it becomes linearly separable, right? So the moment you're shifting to higher dimensions, in this case, it's just 2D to 3D, but in complicated data values, we have to shift over to 10 dimension, 28 dimension, in some cases, dimensions of really high values. So So quantum computers are really helpful in those cases because we have exponential speed up possible. We have we have the possibility of exponential state space in the Hilbert space, right? The next application is topological analysis with the hybrid implementation of both quantum and classical systems. It can make the topological analysis really fast. So to summarize this entire thing, I would say that QML is all about using the powers of quantum computing in classical machine and the paradigm of classical machine learning, putting them together and using it for quantum machine learning. And finally, it's not about the speed up. It's not about solving the problems which classical computers are already good at. If you want image classification, or if you want to detect images in a picture or detect faces in a picture, classical computers are already good at that. We don't need quantum systems for that. We need quantum systems for situations wherein classical systems fail to perform. Okay, this doesn't mean that we think of this world as a quantum simulation and start dodging bullets like Neo in the Matrix. On a final note, I would say in the future we can expect a lot of hybrid quantum classical systems. These kind of architectures will be possible wherein you have QPUs, quantum processing units, just like we have GPUs today. We can have quantum accelerators, which will work hand in hand with classical systems to deliver solutions which are actually not possible with classical systems these days. I'll give you a small demonstration of a simple classifier with Microsoft Q Sharp. Let me just go ahead. So this is the backend.qs Q Sharp file, wherein we are actually defining the classifier structure using the controlled rotation gate. So this is similar to the variational circuit, which we had defined earlier with the parameters phi1. So, and then we are defining the linearly separable model here in the Q Sharp file, and also the classifier for the linearly separable model. Then finally, in the driver program, what we are doing is we are actually generating the synthetic data using random.random. So I've generated the data, 2D data for both the X and Y values, random.random, because I want synthetic data which can easily be classified. And for simplicity, I'm just showing you data which is generated from our end only. So let's visualize this data. We see that it is easily separable with two lines. We have the class 0 as blue, class 1 as red. Now, if you train it using the quantum classification from the backend.qsharp file, and then use the train linearly separable model, using this model, you're training the entire, you're using the data to train the model. And then finally, after the training and the validation is complete, you can see that the miss rate comes out to be 0.00%, which means the accuracy is 100%. So why is this so? Because we've used synthetic data which matches our exact problem statement. So this was it for the basic demonstration. Of course, the code will be available to you guys later on. Thanks for attending this talk, guys. I know this was just a lightning talk, introduction into quantum machine learning. So if you really want some, daily dose or weekly dose of quantum computing and machine learning, please make sure to follow our LinkedIn page. You can just go to bit.ly/qpower LinkedIn and follow our page, and then you can get updates on the real things happening in the world on quantum computers, or some tutorials on quantum machine learning. And also, we are starting a new program for quantum machine learning and quantum computing actually within QPower LinkedIn. And if you would like to sign up for it, it's free and it's in the first week of October. Just go to bit.ly/qpower101. You can sign up for it and we'll get back to you. If you have any questions and I'm not able to take it right now, you can leave an email to me. The email is on the screen. So thank you, guys. Thank you for watching this session. If you have any questions, I can take them up in the chat.
Thanks a lot, Syed, for your wonderful session.
Yeah.
That demo of that Mantis one was really cool. So right now,